Hey everyone, welcome back. And in this video, we're going to continue the discussion that we started a couple of videos ago about tracking and especially using a library called Trackpy in Python. And here we are going to focus a bit on 3D dataset or object tracking, and I am going to use the dataset that is provided by Trackpy as one of their examples, and I'm going to walk you through a few lines of code in terms of how you can go ahead and locate these objects and then track them as a function of time, and finally end up by reporting the diffusion constant, for example. Again, this is exactly the same example that Trackpy guys used it, so go ahead and look up the documentation of Trackpy for even more information. So with that information, let's go ahead and jump into our code. And first thing first, I should let you know that, well, at least I'll leave the link to Trackpy library or as part of the description down here, but it's easy to find. Just go ahead and Google search for it, you'll find it. And there are various examples right here that you can walk through, and each example covers slightly different scenarios. So when you go through all of these, you can kind of put together what, the code for most of the scenarios, I should say. Okay, now what dataset am I going to, again, I'll leave link as part of the description down below. And the way they have this dataset is a bit weird. It's actually a zip file. So let's go ahead and open that first. And in fact, when you open the zip file, when you extract the zip file, you should see a whole bunch of images. In fact, apparently I deleted a lot of them. The images have, I deleted a lot of them because I captured them as a single file, but I left a few, I kept a few to show you guys how the dataset looks like. The file name is file, letter T for timestamp, 30th time, and is z equals to your z stack, and it goes from 1 through 25, and then the time changes in this case from 30 to 31. So they have about 33 time steps, and each stack, z stack, has 25 images, and they look pretty normal if you look at the images. There you go, not high resolution, so you should be able to easily open them, and there you go. These are the blobs in 3D that we need to segment and track. And usually these things can be a bit abstract, so I kind of combined them into a single file, and I opened it in scientific imaging software. I mean, you can actually download Zen Lite version of it for visualization, for basic image processing operations, and of course there is a paid version if you want a lot more capabilities like machine learning and a whole bunch of other stuff as part of Zen. And of course this is, if you're a Zeiss user, Zeiss microscope user, you know what this is exactly. Okay, this can help us open multi-dimensional images, and this is not required for you to do anything that I'm going to show you later on. The reason I opened this is to show you that, okay, this is a single 2D slice from a 3D image, and here it is. That is the 3D image. And how many such images do we have? We have 33 such images, right? So 33 time steps. So if I slide through this in timestamp, you see how the objects are moving around. This is what we are going to track in 3D. So if I switch to the 3D mode, you should be seeing these objects. Let me switch. And there you go. So these are all the objects that we have in 3D. Yeah, and this is at one time. Now if I move the time, you see how these objects are moving around. I hope it gets captured very well as part of this video recording, but this is exactly what's going on. Okay, now that you understand the dataset, let us go ahead and jump onto our colab to continue the discussion. So let's get to colab. First thing first, let's go ahead and connect. And as usual, like I talked about in the last video and the one before that, we are going to start by installing Conda on colab, because we're going to use that Conda to install our Trackpy and PIMS libraries that are required for this exercise. So to do that, first thing first, once it's connected, let me make sure I connect my drive. I mounted the drive and I uploaded the dataset to my drive, so I can go ahead and use that right here. So I don't need the left-hand side. Let me close it, and the font is large enough for you to see. And let us go through this exercise again. Watch this video that I've done maybe more than a couple of months ago on the topic of how to install colab on your, how to install Conda on your colab. So I'm not going to go through that in very much detail. So first thing first, let's find out what Python version is under this notepad. And right now Google Colab is giving us 3.7. So I want to, let's define the environment. So I want to install a mini Conda of version Python 3.7. That's the only reason I found out what Python I have here. It doesn't matter, you can install mini Conda Py 39 or something, but I want to stick with what the natively Colab is providing, and that's exactly what it is. So now I'm going to install the Conda environment, and as you probably know, Conda comes with a few packages already installed, and one of course Python, but in addition to that it comes with basic ones like the core essence packages. On top of that you can install any of the others, which is exactly what we'll be doing pretty in a few minutes anyway. So once this is done, I am going to kill the output. I don't care about it. And let's see where the Conda is installed. There you go. Bin Conda. What version Conda is installed? 4.12.0, because that's exactly what we asked it to do. And now let's go ahead and update Conda update, right? Anytime you kind of do any installation, you always try to do Conda update and then Conda install. So that's what we are trying to do, Conda update, and then we are going to use Conda install, or two packages that we need for this exercise for Trackpy. Okay, so what version Conda we have now? It is 4.13.0. Python should be 3.7.13. And let's have a quick look at the assist path. So we have userlib Python 3.7, we have distribution packages, we have all of this stuff. In addition to that, we want to add to this a path called site packages. So our Conda installation knows exactly where it is. And now let's go ahead and install Trackpy. And I'm installing exactly based on what these guys suggested. Conda update, Conda install, copy and paste this, and then this. So that's exactly what we're doing right there. Conda install Trackpy and then PIMS. Then we are all set to go ahead and continue our regular exercise. So I'm going to pause the video until these two are done. You have seen this a couple of times in the last two videos, so no point in staring at the screen when this is happening. Okay, so we are done installing both of these packages, all set. Now we can focus on our primary task, which is 3D tracking. So let's import the required libraries like matplotlib, numpy, pandas, and PIMS and Trackpy. So let's import those and move down, and now let's go ahead and read our dataset. Now this is where you can use your own reader. So if you have, if you're working with OME TIFF file formats, not many file formats can handle these type of 4-dimensional or multi-dimensional datasets, right? So there are very few. One is, for example, OME TIFF file format. You can do that, and CZI file format or any other proprietary microscope file formats. It's pretty common for you to find them to be very good at handling multidimensional data sets. And PIMS can actually, it has multiple readers to read all kinds of formats. So go ahead and find the right one. In this case, we are going to find image sequence ND. And this, in this example, our data set is a whole bunch of images in a zip drive. That's it. It's got 33 times 25, how many ever? Why 33? 33 timestamps and 25 stacks in each timestamp, right? So that many images in one zip folder. And this way we are actually reading it. And the axis identifiers are Z and T right there. So the timestamp and the T right there. And let's go ahead and run these so we are reading the right data set. Again, you can use your own way. It doesn't matter. Eventually, it needs to be in a NumPy format. That's all it comes down to. So here you can see there are 4 axes. Axis Z has 25 images. Each XYZ data set is like 128 by 128 by 25. And we have 33 such timestamps. We saw that from our data when we went through the file naming system earlier, right? So we know what that is, and these are all unsigned integer 8s. Okay, so you can slice them again. Let's just look at the 0th Z and 0th time. So only the time slice and time slice for specific Z. Let's go ahead and get that and have a quick look, and you can see how they look like. Okay, so now that our data is available, we just need to segment these. And again, you can follow your own, like loading the data set using bioformats, for example, and then using 3D Stardist for segmenting these blobs. But if they are blobs like the ones that you see on the screen, then the regular blob detector can do a pretty decent job. And that's exactly what the tp.locate uses as part of the Trackpy. The locate function actually uses the blob detector. All you need to do is just give it provide the approximate diameter of the blobs that you're looking for. That's it. And in this case, here is the approximate diameter for the blobs, and we are giving them in the range of z, y, x, right? So z is 5 pixels, y is 9, and x is 9. And the reason why it is not 999 all the same is the pixels in this case are not isotropic. They're not of the same size, and this is what their documentation actually recommended. So I'm just going to use this. But if your voxels are isotropic, for example, if you collected that from like an MRI or a computer tomography, then your voxels are isotropic. But if you're actually collecting a slice of image and then slicing the sample and then another image, slicing the sample, another image, then it's tough to get isotropic voxel size. Then you have to kind of do certain tricks to kind of make them isotropic. Okay, so let's go ahead and locate the features. And again, it captures all of this information after the segmentation as part of a pandas data frame. So now you have your ZXY, mass is, I believe that's the brightness over there, size XY, and all the other parameters that these guys actually capture. Well, I mean, the library actually captures when you do the trackpy.locate. This data frame is all we need from this point and on, because it has all the information, and we are going to use that, for example, to paste to show the segmented regions onto your image. For some reason in the notepad, I haven't tested this on my local spider, for example, Anaconda Spider IDE, but at least in the notepad, when I do tp.annotate 3D, I'm not getting anything. It's just blank, so I'm not going to show you anything. And locating, so now that we have done this, for frame 0, we need to actually do that for all the frames, right? We don't want to just stop at frame 0. We need to get this in 3D. So that is exactly what we are trying to do. Batch for all the frames that we have, and diameter in this case 7, 11, and 11. You can change that to 9 and 9 and see what happens. And separation is basically what is the minimum separation between the blobs for it to actually segment them, that in 3D, right? So that's why you have 3 dimensions. That's what the batch actually does. So it's basically a batch locate function. That's it. So it is giving some error. I saw this before. I have no clue what's going on over there. But when I run this the second time, let's see. Yeah, now frame 32. Sorry, I don't know what's going on. If any of the Trackpy guys are watching this video for whatever reason, please verify what that is. It seems to be some temporary issue, because it's when I run this the third time, it's actually running okay. So anyway, one glitch right there. Okay, now that we have our data frame with all the information, now we need to link that to particles, right? To particle trajectories. We need to link it using tp.link. And when we say link, what that means is between frame to frame, we have to find a continuity between a given object in these 2 different frames. That's how it actually tracks it. That's how it actually links it. Okay, this is the same object in the next one. That means you have to provide the vicinity of where it should be looking at in this 3D space. Hey, I'm here in this time stamp, and as the time goes by, I'm slightly there, slightly here, but I'm not going to be over there, right? So what is that neighborhood within which you should be looking for me, right? So that's exactly what we need to provide for tracking. But before doing that, we need to calibrate our pixel size, X, Y, and Z. In this case, this data set, in X and Y, it's 0.21 microns pixel size, and in Z, it's almost 3 times that. It's yeah, I should say almost 4 times that. It's 0.75 microns in Z. So what we're doing here is basically multiplying the values in X, Y, and Z right there with corresponding pixel sizes. So in a way, we are kind of normalizing that, or making this isotropic. Okay, so that is exactly what we are doing down here. Again, if you're working with isotropic, then you're fine. isotropic data sets. Now, this is when we actually go ahead and do tp.link underscore df and then get it done. But again, because the pixel sizes are different, we don't know if tp.link, this column, where is it? Search range, like this parameter, the second parameter, where it shows, okay, what is the neighborhood I should be looking at? We are going to look at 1 pixel, 1.5, 2, and 2.5. I guess in this case, we can call them microns. 1 micron, 1.5 micron, 2 microns, and 2.5 microns, and see which one is actually the best one. So let's go ahead and run that, and we are going to plot that in relative frequency, and let's pick the minimum one right here. This is versus track length. So I am going to take either 0.2 or 0.3, I guess. Where is it? Sorry, not 0.2, 0.3. Where is the 2? Yeah, so any of these is fine, right? I mean, 2 or 3, these two, like this or this. We can replot it to see exactly what the value is. So it's not 1, 2. So let's just say 2 or 2.5 microns according to them. They don't see much of an improvement, so let's go ahead and use a value of 2 right there. You could have directly jumped into, okay, I know that my particle, my gray, the size of these is about 1 micron, right, in Z, and then here 0.2. Maybe I'll just do 3 times that, just to pick the neighborhood distance, or in this case, it would be 6 times that. Yeah, so almost 6 times that. So that's what we are trying to do here. So now all we are doing is linking it with a value of 2, and of course, what is the columns x micro? What is the position? It's x. These are the position columns as part of our data frame F that it's going to look at. Okay, so we have 32 frames and 165 trajectories. And again, I talked about tp.link in the last video, and here everything is exactly the same except we have 3 instead of 2 coordinates to define a particle. That's it. That is the only difference. Otherwise, this refers to the neighborhood distance or how far, right? And this defines basically the center of your object. Okay, now that we have this, now we just need to look at more analytics, and there are many analytics available as part of Trackpy, but a couple of things that most of the time we look at is mean square displacement, and also if you want to look at diffusion coefficient. So those are the two that are kind of demonstrated here. So there are 2 types of mean square displacement. We are going to look at EMSD for now, and again, we can fit that to a straight line because we are going to plot that. Where is it? Let's go ahead and plot it and have a quick look at it. And again, MPP stands for, I forgot. I remember that I read the documentation, but I forgot what that exactly stands for. But if you haven't already calibrated your pixel size right here, which we did, then you can provide a scaling factor right around here using the MPP. Yeah. And this frames per second, we already know in the last exercise we used 24 frames per second. In this case, it's 1 over 0.8582 because that's how frequent these images were collected, these data sets were collected. And lag time is, again, how long do you want me to remember? I think that is what lag time is for an object for going in and out of the region of interest. So there you go. That's the straight line. And if you fit this, is there something that I think, yeah, we can fit that using least squares right here. That is available as part of your NumPy. And just look at the slope. And by the way, the equation for this is your, if you think this is Brownian motion, again, if it is random, and if you would like to calculate the diffusion coefficient, then this is the equation for the Brownian motion. X squared equals to 6 dt, which means if you want to get your diffusion coefficient, then or constant, then you can extract that by fitting this to a straight line, which is exactly what we did. Right here. So there you go. That's fit to a straight line, and the diffusion constant is 0.18 micron squared per second. And you can extract a lot more information. Again, the documentation, go ahead and look at the documentation tutorials, but then the API is something that you may find very useful. Go ahead and look at, it's not that deep actually. There are very few handful of these. If you just go through these, you'll know exactly what functions are available, and more power to you. So thank you very much for watching these videos. Again, please hit the like button, please hit the subscribe button. Let's meet again in the next video.